Okay, let's discuss about how do we represent geometry in graphics. Let's look at a few basic elements which are used to represent geometry in computer graphics. The basic elements are scalars, vectors, and points. Using scalars, vectors, and points, we can build sophisticated objects from these building blocks. So we all know what scalars, vectors, and points are, but we'll do a quick recap. Scalars normally, for for the scope of this course, you can look at them as real numbers, and they uh, they satisfy additivity. I mean, two scalars can be added. Their excess and additive identity. Uh, Also, there's an additive inverse. Like alpha minus alpha will be equal to 0. It also has associative and commutative properties. Vectors, you can look, one of the examples of a vector is something like a velocity. So it has both the magnitude and direction. There's also an identity, additive identity as a zero vector. Also, it has an additive inverse. It satisfies also both associative and commutative property. So issue with scalars is that you can't represent geometry with scalars. It's just like a number. But with vectors, you have a magnitude as well as a direction. But vectors can be located anywhere in space. You don't have a specific location for vectors. So just vectors is not sufficient to represent geometry. So for that, we look at points along with vectors. So a point normally fixes a point in space. So a point plus a vector gives you another point. A vector can be represented. So there's a point P and there's a vector V, and P plus V will be the point Q. So the vector can be represented as alpha, I mean Q minus P. Uh, this vector can also be scaled. So these are the basic elements. So vectors along with points and along with scalars, scaled versions of vectors along with points will represent geometry. So these are the building blocks of geometry. And for the graphics pipeline, well, normally we deal with affine spaces. Affine spaces is a point plus a vector space. So normally this point is the origin. And the operations which we are performing in defined spaces is vector-vector addition, scalar-vector multiplication, point vector addition, and scalar-scalar operations. We'll look at affine spaces with more detail. Okay, let's look at the basic geometry, which are lines. So the representation of lines in graphics is by using an affine transformation of a point and a vector. So a P of alpha, where alpha is a parameter which actually parameterizes how far we are in the line, is given by a point P0 plus alpha times d, where d is the direction of a vector. A set of all points reached while walking from P in the direction of vector d will constitute a line. So if you have a position P0 and if you have direction d, we move alpha alpha times d, or alpha steps in that direction from that point, then you end up getting a line. So there are multiple representations of line, which is not very important for this course. We'll currently skip this. Now we'll look at line segments. Line segments, we've already seen lines. Line segments are more confined versions of lines. If you use 2 points to define a vector, then P of alpha is equal to Q plus alpha times V, which we've already seen earlier. But we've also seen a vector can be represented as a difference between 2 points, right? So Q can be represented as, sorry, V can be represented as R minus Q. So Q is alpha times R minus Q. I mean, Q plus P of alpha is equal to Q plus alpha times R minus Q. If you rearrange this, you'll get alpha times R plus 1 minus alpha times Q. So this is actually the parametric form of a line segment. So here, the alpha values are between 0 and 1. Then 1 minus alpha also lies between 0 and 1. So we get all the points in the line segment joining R and Q by varying alpha between 0 and 1. This is how we represent the line segment. So note it's P of alpha is equal to alpha times R plus 1 minus alpha times Q, where R and Q are 2 points on the line segment. I mean, 2 ends of the line segment, to be precise. So this is actually, we've represented the points of on a line segment by using the combination of as a sum of 2 points. Such sums are called affine sums. So when we are representing a point P as an affine sum of multiple points, then such sums are called affine sums, where alpha 1 plus alpha 2 plus alpha n gives a 1. So the sum of all the coefficients or the scalars which correspondingly scale these points, they add up to 1. Such sums are called affine sums. Okay, P is a affine sum of points, P1, P2, etc., Pn, where alpha 1 plus alpha 2 plus alpha n add up to 1. Then P lies in, if P is represented as an affine sum of points, P1, P2, Pn, then we can also say that P lies in the affine hull of the points P1, P2, etc., Pn. So there's a more specific case. If all the alpha i's are greater than 0, so in this case, note that this can be also negative. Alphas can be negative. But if all the alphas are greater than 0, and also if they add up to 1, then such an affine sum leads to, then when we say P lies in the convex hull of these points of P1, P2, P3. So the two conditions which has to be satisfied for the convex hull. First is that all the coefficients of the points should add up to 1, and next is all the coefficients should be greater than or equal to 0. So convexity, in terms of geometry, how do you expect explain convexity is an object is said to be convex if and only if any 2 points in the object uh, on the line segment between these points also. Okay. If and only if you take any 2 points on the object, all points in the line segment joining these 2 points also lies inside the object. So this is convex. So if you take any 2 points on this object and join them using a line segment, the line segment lies within the object, but this shape on the right is not a convex shape. So we've already seen what the convex hull is in terms of the definition with respect to points, but geometrically, convex hull can be viewed as a smallest convex object containing points P1, etc., Pn. So if you have multiple points Pn, the kind of a wrap around this points, which contains all these points, can be treated as the convex hull of these points. Okay, that's a discussion about lines. Now we'll look at planes in the next session.